So in this tutorial I would like to connect signals to a very interesting application, and that is music. Music is why I got interested in signals myself. And if you remember high school physics, we studied two properties of sound. Okay, one is loudness. Okay, you can see that here, loudness. Okay, and the other one is pitch. And we also learned that if a sound is represented as a signal, okay, if it is represented as a signal, loudness translates into what is known as amplitude. Okay, so I have a sine wave here. I've taken this from Wikipedia, and the louder my sound, the louder would be the height of this sine. Okay, so if my sound was louder, it would be probably the amplitude would be maybe 2 or maybe 10, depends on how loud it is. Okay, or if it was softer, it would be probably 0.5 or 0.25, something like that. Okay, just to give you an example. So that's loudness. Okay, we also learned in high school, we also learned about pitch. Okay, so if you have a high note or if you have a low note, what would that translate to in the signal? So we learned that a pitch corresponds to frequency of the signal. So the higher the frequency, the higher the pitch of this of the sound. So probably a high note, a higher octave would have a higher frequency, and a low octave note would have a lower frequency. Okay, so that's what that we learned that loudness and pitch characterizes a sound. But suppose you take, let's say, a violin, and suppose you take a guitar. Okay, and suppose you play exactly the same note at exactly the same octave. Okay, and at exactly the same loudness. Okay, you know that you can differentiate between a guitar and a violin and a trumpet, even if they are playing exactly the same note. Okay, you know which instrument is making what sound. Okay, so why is that? To explain that, we have a third property, and it's called timbre. Timbre refers to the shape of the wave. Okay, so maybe our wave looks like this. Okay, maybe our wave looks like this, or maybe our wave looks probably, let me just make this a little bigger. Okay, so maybe our wave looks something like this. Okay, I'm just drawing different shapes. Or maybe our wave is just one square wave like this. Okay, so depending on the shape of the wave, the sound, even though it is exactly the same frequency, imagine that these three have the same frequency. Okay, and even though they have approximately the same frequency, they would make a different sound. They would sound different. Our ears would perceive them as different. So the reason for that is the shape of the wave. Okay, and these shapes are quite complicated. They're not like our simple sine which we see over here. Okay, so it makes it a little difficult to study these complicated curves. But that's where Fourier analysis comes in. So in lecture we learned that any periodic signal, okay, or rather almost any periodic signal, okay, given certain conditions, almost any periodic signal can be represented in terms of simple basic sine waves of different frequencies. In fact, if you have let's assume this was a 20 hertz square wave, you can represent this as a superposition of sines. Okay, and the sine waves would have frequencies of multiples of 20 hertz. So if you remember frequency analysis, if you remember the formula for if you remember the Fourier series. Okay, the Fourier series has, the first term would have the same frequency as the original, because k is equal to 1. Okay, so for k equal to 1 you would have the same frequency, and for multiples, for the next coefficients, you'd have k equal to 2, k equal to 3, and so on. So you'd have the higher frequency. So that's what Fourier analysis gives us. So I'll just show you the square wave. Okay, and here we have a square wave. Let's say this is a 10 hertz square wave. Okay, just for just to take an example. So let's call this let's say this is a 10 hertz square wave, and if I perform Fourier analysis on this, if I find out the Fourier series, okay, our first term in that Fourier series would be this sine wave. Okay, and this would also have a 10 hertz frequency. Okay, so this is our sine wave. Our second term in that Fourier series would be a 20 hertz sine wave. Okay, and this picture is from Wikipedia again. I was too lazy to make my own diagrams, I guess. So if I take the second component, the second component would be something like this. It's not exactly right, but it would be double the frequency. Okay, so it would be double the frequency, something like this. Okay, yeah, this is right. So it would be double the frequency like this. Okay, and of some particular amplitude depending on what Fourier coefficient you get. So you add these two up, you'll get this, right? And this was shown in lecture as well. So you add a third term, and the third term would be 3 times of the frequency, so this would be 30 Hertz. Okay, and you'd get this if you add up the third term. You add up the fourth term, okay, which would be 40 Hertz. Okay, and you add this up, you'll get this curve. So you add up more and more terms, you'll get what looks closer to our it would look closer to our square wave. Okay, and we saw that demo in the lecture. Okay, so the point is, to get a signal of any shape, you break it down into Fourier series. You find out the Fourier series of that wave, and once you find out the Fourier series of the wave, you know the fundamental sine waves. Okay, so this brings us to a concept of frequency spectrum. So what frequency spectrum means is that we know the signs. Okay, we know what signs are there in the so let me just write that down for you. So for that square wave, we would have something like A0 times sine of 2 pi 10 Hertz. Okay, plus A1 times, let's call this A1, A2 times sine of 2 star pi star 20 Hertz. Okay, and so on. So you would have a 30 Hertz term, 40 Hertz term. So what I'm trying to say is, there are sines. Okay, so there is a 10 Hertz component. Okay, this is a 20 Hertz component. Okay, and the 10 Hertz component has an amplitude of A1. Okay, and the 20 Hertz component has an amplitude of A2. Okay, we can see the 10 Hertz component right here. So the 10 Hertz component has this amplitude, right? So that would be my coefficient A1, right? Similarly, my 20 Hertz component would have a different coefficient. Okay, 30 Hertz component would have a different coefficient, and 40 Hertz would have a different coefficient, and so on. Okay, so those are my so what I'm trying to say is that this is a frequency component. 10 Hertz is a frequency component, and that component has this amplitude. Okay, and my 20 Hertz component has a different amplitude. Okay, and so on. So that's what Fourier analysis gives us. It gives us what frequencies are there, what sinusoids are there, so what frequencies are there, and what is the amplitude of each sine. You add up all of these together, and you get your funny looking signal, like this or like this or like this. Okay, so that is Fourier analysis. So let's move on to some real instruments. I just have a keyboard with me, so I'll use that keyboard to generate the sounds of a violin, a guitar, and a trumpet. So we will actually see the frequency spectrum. Okay, like I told you, the frequency spectrum will tell us which frequencies are there. Okay, that sine 10, sine 20 Hertz, the 20 Hertz sine, the 30 Hertz sine, 40 Hertz sine. So what all is there, and the amplitude of each of those sines. So on the horizontal axis over here, okay, there are two graphs. Okay, the top graph will tell us the time signal. So the signal as it varies with time, that's the normal time domain, the representation we're all familiar with. Okay, so a sine would look, this wavy, look like a wave like this. Okay, but the lower graph, okay, is what we are more interested in. Okay, I'll talk about both graphs later on. So the lower graph will tell us the frequency spectrum. It will the horizontal axis gives us the frequency. So you can see I'm not sure if it's visible. I doubt it's visible. Let me see if I can zoom in. So okay, so I'm not able to. Okay, anyway, so if the bottom, the horizontal axis is the frequency. Okay, and the vertical axis is the height of that frequency, is the size, the amplitude of that sine function. Okay, in the Fourier series, the amplitude of that sine function is on the vertical axis. Okay, and that's in dB. Okay, so let's decibel. So let's just look at a violin. I'm going to play the C note. That's not C. Okay, sorry. Okay, so that's the C note. Okay, so and let me just see if I'm playing the right one. Yes, I'm playing the right one. Okay, so this is the C note of the violin. Okay, I want you to concentrate on the shape of the wave. Okay, let me see if I can increase the amplitude. Yeah, so I made it a little louder for the computer. So have a look at the shape of the wave. Okay, and look at the spectrum as well. Okay, so that's the spectrum of the violin, and that's the shape of the wave of the violin. I'll discuss both shortly. Let's move on to the guitar. So we have, okay, that's the guitar, and if you remember the shape of the violin, the guitar looks completely different. The spectrum of the guitar also looks completely different. Okay, let me just move to the violin quickly. You can see that's the violin, and this is the guitar. Okay, they're different, they're completely different. So okay, so that's the guitar. Let's also see the trumpet. Okay, since that also has a sustained sound. Okay, totally different shapes. So let's move back to the violin and compare that. Okay, quite different. So trumpet and violin. Okay, so there's a difference, and that's for the real-time demo. Let's actually look at each of these in detail. So what you see here is the time graph. Okay, so this over here is the violin. Okay, quite different. This is the guitar. You can see the shape is completely different from the violin. This is the violin, this is the guitar, and this is the trumpet. Three completely different shapes. Okay, and that's what I wanted to emphasize. So the shape is different, and that gives us those different sounds which we saw, right? So which we heard rather. So that is the shape, and that shape obviously corresponds to different frequencies. So here is the frequency spectrum. I had already recorded these. So you can see here that this is my coefficient A sub k. Okay, that's the height of the coefficient. It's about minus 25 dB. This is about let's say probably 34 or 33 dB, minus 34 or 33 dB. This is minus 25 dB. This is probably minus 27.5 dB. Okay, and so on. And if you look at the horizontal axis, okay, is this visible? I hope it's visible. Okay, this is about 500, right? So if I actually go up, it's slightly above 500. Let's just call it 500. So what I'm trying to say is that there is a 500 hertz component. So we have sine of 2 into pi into 500. Okay, that's the sine multiplied by this minus 25 dB. Okay, if we convert into absolute number. So that is one component. You can see that there is a 1000 hertz component. That's a 1 kilohertz component. Okay, and there is a 1.5 kilohertz, 2 kilohertz, 2.5, 3, 3.54, and so on. Okay, so those are various components. Okay, and next I'll look at, so this was for the violin. Okay, and you can see this has a frequency spectrum like this. So if I just take a brush, and so it looks something like this, right? So I'll just show you, just to show you the difference between the three. Okay, I'm just joining these peaks together just to show you that, and it's something like this. Okay, anyway, so this is my violin. Let's move on to the guitar. The guitar has a slightly different frequency spectrum. It has a 250 hertz component as well. Okay, and remember, this is the same note. This is the same C note I played for all three instruments, but it has a 250 hertz component. So I'm guessing that the violin also had a 250 hertz component, but it was quite small. Okay, it was somewhere here, and it got muffled by the noise. There is some noise, I guess. So this is the guitar. The guitar has a huge 250 hertz component. I'm guessing it has something. It has something over here, but we'll ignore that for now. Okay, so we have this 250 hertz component, and it has a very high amplitude. Okay, above minus 15. It's probably minus 12.5 dB or minus 11 dB. Okay, then we have the 500 hertz component, which is close to 30 dB, minus 30 dB. We have a 750 hertz component. We have 1 kilohertz, 1.25, 1.5, and 1.75, and so on. Okay, so that's the guitar, and the guitar has something like this, right? So it goes down like this. Okay, so let's just Assume this is the frequency spectrum. So this is the frequency spectrum approximately for a guitar. Okay. So finally we'll move on to the trumpet. Notice that the violin, okay, and the trumpet have very crisp peaks. Okay, they have very sharp peaks, whereas the guitar has these multiple middle frequency. That's because the guitar has more harmonics, whereas the violin, at least the synthesized version of the violin, because remember, okay, what I've done is I've connected a keyboard to my computer. I don't have a real violin and I don't have a real trumpet. I do have guitar though, but I'm using the keyboard. Okay, so this is synthesized sound. So the sound for the guitar, the violin and the trumpet which the keyboard produces, they have very sharp frequencies over here, so in multiples of 500 hertz, whereas the guitar has sharp frequencies at 250 hertz, in multiples of 250 hertz. So like I said, this is the frequency spectrum for guitar, and this is the frequency spectrum of a violin. You can see this as 500, 1000, 1.5 kilohertz, 2 kilohertz, 2.5, and so on, and it goes on like this. So the shapes are different. Let me just zoom out. You can see that the shapes are different. I hope that red line is visible. Okay, so the shape is different, and because the frequency spectrum is different, the instruments sound different. So why is this important? A lot of times in the post-processing, after you record some music and you want to process it, you might want to boost the sound of, let's say, drums, or you may want to make the guitar sound louder, or you may want to make a person's voice sound louder. So what you do is you know the frequency spectrum of that particular person, or you know the frequency spectrum of that particular instrument, and you boost only those frequencies. You increase the amplitude of only those frequencies, okay, and that causes that particular instrument to sound louder. Okay, so that's one application. Another application of frequency analysis is removing noise. I'm not sure if it's heard in this video, but in my previous videos you would hear a lot of background noise in my recording. So that's my CPU fan. So in a real recording studio you wouldn't have that, but it's possible you would have some noise. The thermal noise of the microphone, you have noise in the amplifier, because the amplifier consists of transistors, and the transistors has electrons hitting each other. Okay, that's how the transistor works, and that causes thermal noise. So you want to reduce the effects of those noise. You want to reduce the distortion. So here, that's also where frequency analysis comes into is very useful. And I wanted to show you how music and signals analysis is related, and I hope you like this video.